Good morning. In the lesson today, we're going to begin our look at factoring. And in this lesson, we'll review two main types of factoring. Common factoring, where you simply identify the greatest common factor of the terms and then remove that greatest common factor. Difference of squares factoring, which takes a difference between two perfect square terms and expresses that as the product of a plus b and a minus b. So I thought that to review this, I would just go through many of the even numbered problems from your textbook. This would be exercises 6.2. So here's our first example. We have 5b plus 5a. The greatest common factor of those terms is 5. They are both divisible by 5, and dividing 5b by 5 will leave us with b. Then you put the plus sign in the middle. Dividing 5a by 5 will leave you with a. So this is the factored expression. Of course, if you were going to use multiplication and open up that bracket, you would get this back. The greatest common factor in problem 8 is 3. So now we simply divide each of these terms by 3, and that will give us x squared minus 2. In number 12, each term is divisible by 5, but each term is also divisible by r. So the greatest common factor is 5r. 5r squared divided by r is r. Put in the middle sign. 20rh divided by 5r would be 4h. Problem 20 has 3 terms. What's the greatest common factor for all 3 terms? All 3 terms are divisible by 3, and a is also common. So 3a is the greatest common factor. And now we divide all terms by 3a, and we're going to get here 9ab, here 8b, and here 3. So this is what the factored expression will look like. Okay, so those were 4 examples of common factoring only. Okay, now we have our first example of difference of squares factoring. This is a perfect square, and 25 is also a perfect square since it is 5 squared. So that means we can write, using the formula, r plus 5, r minus 5. And of course, if you were to expand this, you would have 4 terms initially, r squared minus 5r plus 5r minus 25. The middle 2 terms would cancel each other out, and that's why these expressions are equal. Okay, this next one. Do we have 2 perfect squares? Yes, because the square root of 49 is 7. The square root of z to the 4 is z squared. And so our factors are 7 plus z squared, 7 minus z squared. Okay, our next example here. We have 324 z squared minus 4. Now this example is a good reminder that what we should do first is remove any common factors. Because in fact, both of these 2 terms, the terms of course are separated by the subtraction sign, Both terms are divisible by 4, so we should begin by removing that common factor of 4. That would leave us here with 81z squared minus 1. So that is definitely our very first step. Now, following that, we can leave the 4 here and use difference of squares factoring on this binomial. And that's because 81z squared is the square of 9z. And 1 is the square of 1. So we will have here 9z plus 1, 9z minus 1. Okay, and again, the square root of 81z squared is 9z. The square root of 1 is 1. Okay, number 30. What is the square root of 36s squared? It is 6s. And so that means that we will have 6s here, 6s here. One will have a plus sign, the other a minus sign. And now we need the square root of 121t squared. And that is 11t. So 11t is here, and 11t is also here. Okay, and of course there was no common factor for 36 and 121. There is no number that divides into both 36 and 121, so we could go right away to taking the square root of these terms. Okay, number 32. Here's the original question provided in your textbook. Now there is no common factor for these terms. This is a perfect square though. 36a squared b squared is the square of 6ab. This is also a perfect square. The square root of 169c squared is 13c. But the key is there is no such thing as sum of squares factoring. There is only difference of squares factoring, meaning a subtraction sign between the terms. So in fact, this first expression with the plus sign between the terms is non-factorable. We call it prime. On the other hand, if I change the question by putting a subtraction sign here, now we can do this. The square root of the first term is 6ab. Put a plus sign here, put a minus sign here. The square root of the second term, 13c. And now we have this expression fully factored. Okay, this next one, we have to realize here that 1 is the square of 1. So we do indeed have a difference of two perfect squares. This one's already written as a perfect square. And so we can go right to using the formula, but I'm going to use a different bracket, okay? A different bracket because I already have a round one. So we take the square root of this first term, and the square root of a minus b all squared is just a minus b. So we'll have a minus b here and a minus b here. And then one term will have a plus sign and the other will have a minus sign. The square root of 1 is 1. So that means we'll have a 1 here and a 1 here. And actually, that's about all we can do, except we can remove these brackets now around a minus b. So the first term just becomes a minus b plus 1. And the second is a minus b minus 1, like that. Okay, number 36. 5 is not a perfect square. Okay, so that might remind you to first common factor the terms. So 5 is common to both terms. Let's divide each of these terms by 5. We will have a squared minus 25 once we do that. Now the 5 can remain here, and we'll use difference of squares on this binomial. The square root of a squared is a. Put a plus sign, put a minus sign. The square root of 25 is 5. Okay, and if you wanted to check these, again, remember you use multiplication. So you would multiply these two binomials together first. You'd find that you'd get a squared minus 25 because the middle two terms would cancel. Then you could distribute the 5, and of course you'd get back the original. So multiplication is always the way to check your factoring. Okay, a few more examples. Here we have 28x squared minus 700y squared. And we want to begin by removing the largest common factor. Now, both of these terms are divisible by 7. That would leave you 4 and 100. But 4 and 100 are also each divisible by 4. So, in fact, what you should do is remove 28. It is the largest common factor here. And this will give you x squared minus 25y squared. Now, if you had only removed 7, and you would be left with 4x squared minus 100y squared, you could still remove that common factor of 4 in your next step. Okay, so it's not a disaster if you don't remove the largest common factor at the beginning. Now I do have perfect squares here and subtraction between them. The square root of x squared is x plus minus the square root of 25y squared is 5y. Okay, problem 40. This is one term, this is a second term, and a is common to both of those terms. So we begin by removing a. And that leaves x plus 2 all squared minus y squared. Okay, so the a is, removed here and here, in other words. And now, inside the bracket, we do have the difference of two perfect squares. The square root of the first term is x plus 2. One of these has a plus, the other a minus, and the square root of y squared is y. And you could leave it like this, although in the final answer, normally you would see this term written x plus y plus 2. And this one, x minus y plus 2, like that. So generally, the variables first. Okay, let's look at this problem, 42. We do have a difference of two perfect squares. The square root of y to the 4 is y squared plus minus the square root of 81 is 9. And that is perfect. However, one of these terms can be factored fully. Again, one of these terms can be factored again. It's not this one because of the plus sign. It's this one. This, again, is a difference of two perfect squares. So the first term stays as it is, but this is factored again. The square root of y squared is y plus minus the square root of 9 is 3. Okay, so the second binomial here is factored further. And now we have our final answer. Problem 44. Take out the 2 as the common factor. After that, use difference of squares. What's the square root of x to the 4? It's x squared. Plus, minus, what's the square root of 4y to the 4? It's 2y squared. Unlike the previous example, this is not factorable again, and that's because 2 is not a perfect square. The square root of 2 is not a whole number. So this one is now finished. These last 2 examples are rather strange. We have 4 terms here. In this one, it doesn't appear that anything is common to all of the terms at all. So what we do instead is we group the first 2 together. Common to the first 2 terms is m. Now we group the last 2 terms. What's common to these terms? Nothing but negative n. When you divide each term by negative n, you will have r plus n here. So this is what we wanted to happen. We have a binomial now that's common. So the binomial is removed as the common factor. If that binomial is removed, the second factor is m minus n. You'll notice that if you do here first, outside, inside, last, you'll get back this line here. Okay, and this one is similar except that y is common to all terms. So first we start by taking that out. After that, now we can try to do our grouping. What's common to the first 2 terms? Absolutely nothing. But we remove 1 as the common factor there. Now the last 2 terms, what is common to these terms? 6y squared. So we take out positive 6y squared. Dividing these terms by 6y squared will leave us with 2 minus y. Okay, and again, this is what we were after. So after the term y that was common everywhere, we now have 2 minus y as the common binomial. If 2 minus y is removed from inside here, we'll have 1 plus 6y squared as the second factor. Okay, so I know these 2 are quite different. It's kind of an introduction to the factoring of trinomials that we'll be moving towards shortly. Okay, so thanks for watching all of these examples. Please try the recommended homework that I've posted for you in Blackboard. Thank you. Have a good day.